mathematicians, welcome to part 4 video of Nbhm PhD questions. We want to do 100 problems. This video we see problems 40, 41 to 50. Okay, so let P be a odd prime. Find the number of non-zero square numbers in FP. Okay, so square number means like any number of the form y square for some y belongs to FP. Okay, if you take y to be 0, then y square is 0, but we want non-zero square numbers. Let's see how to do this problem. Okay, if it is a field of order P prime number, then it is isomorphic to ZP. I mean, we can take the elements of FP to be 0, 1, 1 up to P minus 1. Now, here we make an important observation. Consider P minus alpha whole square, where alpha is an element of ZP. Okay. Then P minus alpha the whole square equal to P square minus 2P alpha plus alpha square. Now these two numbers are multiples of P. Therefore they are 0. So we get P minus alpha the whole square equal to alpha square. So what we are observing is we don't one square is equal to P minus 1 square. Okay. Note that in ZP we have elements between 0 to P minus 1, but 0 we don't want to consider because we want non-zero squares. Now 1 square is equal to P minus 1 square. So these two numbers will give us same squares. Okay, so when you square them, we're going to give them same squares. Okay, so these two numbers square will give you same square. Okay, so if you keep going like this, then P minus 1 by 2. This is an if P is so note that P is odd. If you can, it's given that P is odd prime. Here only we are using that fact that P is an odd prime. So then this is like uh, you can we can step by step we can go up to here. Okay, so now this is one square. I mean, like the square of these two numbers will give us the same square. Again, square of these two numbers will give us same square. Finally, square of this number will give us the same square. So there are, you see, 1, 2 up to P minus 1 by 2 numbers are there. If you want to do an example, take Z7. Then this is 1 square equal to 6 square, 2 square equal to 5 square, 3 square equal to 4 square. Therefore, this 7 minus 1 by 2 is 3. So the only distinct square numbers are 1 square, 2 square, 3 square. There are only 3 square numbers. Okay. Therefore, answer is P minus 1 by 2. Okay. Now next, find a generator of F7 star. Okay, so now F7 is a field, so it is a group with respect to addition and multiplication. Again, we identify F7 with Z7. Okay, so if it is a finite field, then its multiplicative group is cyclic. Even you take any field, if you take the finite subgroup of multiplicative group of a field, that will always be cyclic. Okay, so in particular this multiplicative group is cyclic, so we want to know the generators. So we have to look at the units. Sorry, we don't need to look at units. So this was a typo. So we should look at Z7 star. Okay, this is a cyclic group with respect to multiplication modulo 7. So what are the generators? So now the elements are 1, 2, 3, 4, 5, 6 with respect to multiplication modulo 7. Now here, since the number is very small, we can explicitly you can calculate the powers, and you will see that 3 and 5 are the only divisors, only generators. And you see this is a cyclic group of order 6, so it is isomorphic to Z6. Zn has pi of n generators and pi of 6 is 2. Therefore this group should have only 2 generators, and 3 and 5 are precisely the generators. Okay, just keep multiplying with itself, you will see that these two numbers actually giving you all these other elements of the group. Okay, let's move on to the next group, next problem. So A belongs to M3 of R, be a symmetric matrix whose eigenvalues are 1, 1, 3. Express A inverse in the form of alpha I plus beta A. Usually there is in the previous year there is a problem in which you have to express A inverse as alpha I beta A plus gamma A square also, if it is a 3 by 3 matrix. But here it is A square is missing. So I mean, this problem is one even though looks like the previous year simple problem, but this problem one step there is a tricky. Okay. So now the if 1, 1, 3 are the eigenvalues, then the characteristic polynomial PA of x is x minus 1 the whole square into x minus 3. Now, since matrix is symmetric, its the matrix is diagonalizable. Therefore, its minimal polynomial should be product of distinct linear factors. So, we get minimal polynomial is x minus 1 into x minus 3, and a should satisfy the minimal polynomial. So, a square minus 4a plus 3i equal to 0. So, from this, if you calculate 3i, you get minus a square plus 4a, and if you multiply a inverse from the left side, you get a inverse equal to 1 by 3 times minus a plus 4i. From this, you can pick alpha and beta. Alpha is coefficient of I, so coefficient of I is 4 by 3, and beta is coefficient of a. Coefficient of a is minus 1 by 3, and this is the right answer. Okay, let's do 1.8. Let a belongs to M and R. Which are the following statements are true? If a power 2n equal to 0, then a power n is equal to 0. Let's see. If a power 2n is 0, that means that it is a nilpotent matrix. N by n nilpotent matrix. So every n by n nilpotent matrix has its all the eigenvalues are 0. Therefore, its characteristic polynomial is x power n. Again, by Cayley-Hamilton theorem, every matrix satisfies its characteristic polynomial. So we get a power n equal to 0. Okay, next option. If it is a n by n matrix, n greater than or equal to 2, and if a square equal to I, then a equal to plus or minus I. That is not necessarily 2. For example, we take this 3 by 3 matrix. Okay, and if you take the square of this matrix, then you will get identity matrix, but this is neither identity nor minus identity. And for option C, uh, so we again consider the same matrix. So it is a 3 by 3 matrix. Okay, we have to we claim that a power 2n equal to I. That means that we have to calculate sixth power of this matrix. So clearly sixth power of this matrix is identity. Therefore, this matrix satisfies the condition of a power 2n equal to I. They are saying that if a matrix satisfies a power 2n equal to I, then a power n equal to plus or minus I. Let's calculate a cube of this matrix. So 1 0 0 0 minus 1 0 0 0 1 whole cube. You can see that you will get back the same matrix 0 minus 1 0 0 0 1. Okay, and again this is not equal to they are saying that a cube will be plus or minus I, but we are not getting a cube plus or minus I. Okay, therefore the last option is also false. Only this option is true, these options are false. So let's move on to the next problem. Which of the following statements are true? There does not exist a diagonal matrix A. There does not exist a non-diagonal matrix A such that A cube equal to I. Whenever they are asking for A power n equal to I, always look at the rotation matrices. Okay, this is rotation by 2 pi by 3. So rotation by 360 degree by 3, that is rotation by 120 degree. If you rotate by 120 degree, a vector like it will first go to 120 degree, then 240 degree, then it will come to 360 degree. So third time it will come back to its identity. So and you will get a non-diagonal matrix. Okay, it is a 2 by 2 non-diagonal matrix whose cube will be identity. Therefore they are saying there does not exist, but there exists. Therefore this option is wrong. Second is there exists a non-diagonal matrix which is diagonalizable over R and diagonalizable over R, which is such that A cube equal to I. Okay, equal to I. This is what we want. We claim that this is not possible. So if A satisfies A cube equal to I, note that A is a 2 by 2 matrix. So then A satisfies x cube minus 1, but x cube minus 1 equal to x minus 1 into x square plus x plus 1. Okay, so this is a cyclotomic polynomial. This is a first cyclotomic polynomial. Read about cyclotomic polynomials. It is very important concept for Nbhm exam. Now, if A satisfies this polynomial, then minimal polynomial of A will divide this polynomial. Minimal polynomial divides every polynomial satisfied by A. So, so this implies that minimal polynomial of A should be either this polynomial or this polynomial, because these are the only two polynomial dividing this polynomial. Okay, minimal polynomial cannot be equal to this polynomial because it is a 2 by 2 matrix. Okay, so if it's a 2 by 2 matrix, then its minimal polynomial can be of at most degree 2. Okay, now if this is the minimal polynomial, then then we get A equal to identity. Okay, you just substitute the matrix A here, you get A equal to identity. Therefore, this is not possible. Therefore, this should be the minimal polynomial. Okay, but this is already degree 2 polynomial. Okay, if it is a 2 by 2 matrix, if the degree of the minimal polynomial is 2, then that should be the characteristic polynomial also. Now, if you look at the roots of this polynomial, so now, so this is a factor of x cube minus 1, right? So, these roots of this polynomial are cube root of unity. So, 1 omega omega square. If you sum if you sum all of them, 1 plus omega square. So, this is equal to sum of the roots, sum of the roots of this polynomial. So, sum of the roots of the polynomial is coefficient of x square, but there is no coefficient of x square, so you get this roots is 0. Also, 1 is a root of this term. Therefore, this w and w square, the primitive third root of unity, they are roots of this polynomial. Okay, therefore, if this is the characteristic polynomial of A, then the eigenvalues are this w and w square, primitive third root of unity, they are complex roots. Therefore, we conclude that if a matrix satisfies A cube equal to I and if it is non-diagonal, its eigenvalues are primitive third root of unity. In particular, they are complex number, therefore they cannot be diagonalizable over R. Okay, so let's come to the last option, that is true. So there exists a non-diagonal matrix A belongs to M to R and A cube equal to I such that trace of A equal to minus 1. This is actually always true because we just saw that the eigenvalues are W and W square, but 1 plus W square equal to 0. That's what we saw here. Therefore, W plus W square equal to minus 1. Sum of the eigenvalues is the trace, but eigenvalues are W and W square are the eigenvalues. Therefore, their sum is minus 1. Therefore, option C is true. Okay, let's go move on to the next problem. Let W be the subspace of M and R consisting of all matrices whose trace is 0, and we define an inner product in the matrices. It is like usual inner product. You take a matrix and you visualize as a vector in R power n square, then use the usual inner product from R power n. So this is W, set of all trace 0 matrices. We want to identify W perp. Okay, so let's see how to do it. So you take a n by n matrix, then this matrix A can be written as A minus, maybe let me just change the color. So A minus diagonal trace of A by n, trace of A by n, trace of A by n. So I subtract a scalar matrix whose diagonal entries are trace A by n, and I add back that diagonal matrix. Okay, therefore A can be written as, so A equal to this matrix. Okay, this is one matrix, this is another matrix. Okay, now, so if you look at this matrix I take to be B, this matrix I take to be C. Okay, now note that if you take the inner product, using this inner product, if you calculate, you will see that these two elements are orthogonal to each other. Okay, because the way we have defined it, you can see that. So the inner product is usual, like first in one, so you have to take the 1 entry with 1 entry, then 1 2 entry with 1 2 entry. You see, this is how the inner product is defined. So for example, like if it is a 2 by 2 case, then 1 2 3 4, say 5 6 7 8, their inner product is 1 into 5 plus 2 into 6 plus 3 into 7 plus 4 into 8. This is the inner product, usual inner product. Okay, so likewise, you here also you calculate the inner product, you will see that B is perpendicular to C. This matrix is perpendicular to this matrix. That means that their inner product is 0. Now, since A equal to A minus trace A by n times I, this is a scalar matrix. Okay, so trace of B will be trace of A minus the trace of this matrix. So trace of this matrix will be n times trace A by n. So actually this is trace A. This n get cancelled. So we get trace of B is 0. So this matrix has trace 0. Therefore, what we are getting is, if you take an arbitrary matrix in A, you can write it as a trace 0 matrix plus a scalar matrix, and these two are orthogonal to each other. Okay, therefore we conclude that M and R is W direct sum scalar matrices, and this should be the perp. I mean, sorry, this should be the W pair because in this decomposition, this matrix is orthogonal to this matrix. Okay, take some simple example of a matrix A, then form this scalar matrix. You subtract it, you form a matrix B, and form the matrix C, and you do the inner product like this. You will see that they are perpendicular to each other. Okay. So every matrix here can be written as a matrix here plus a matrix here, and the decomposition is unique. Also, this element is orthogonal to this element in the decomposition. Therefore, uh, it is a like orthogonal direction. Okay, let's go to the next problem. Very important problem. Write down the minimal polynomial of a matrix, n by n matrix, whose ijth entry is given by 1 if sum of the indices is n plus 1, 0 otherwise. So let's do case by case. So if n equal to 2, note that this is 1 1 1 2 2 1 3 3. We want the sum of the indices 3, 2 plus 1. So these are the only two entries. Okay, there we have 1, otherwise it is 0. Therefore, okay, let's do the 3 by 3 case. So these are the places where sum of the indices is 4. Therefore, here we have 1. Next 4 by 4 case, you can see that here sum of the indices is 5. Okay, so now we get the idea. So basically in this there is a special name for this diagonal, maybe anti-diagonal, I think. So in this anti-diagonal you have every entry should be 1. Okay, so now if you noticed, so this in this matrix, so this is E1, this is E2, right, the standard basis. So in the place of 1 we have E2, in the second place you have E1. Therefore this is corresponds to the permutation 1 2. In place of 1 you have 2, in place of 2 you have 1. So this is a permutation matrix, corresponds to this permutation. So if you apply this permutation to the rows of 2 by 2 identity matrix, you get this permutation. Similarly here, in place of 1 you have E3, in place of 3 you have U1, in place of 2 you have E2. So 1 goes to 3, 3 goes to 1, 2 goes to 2. So for this permutation, if you apply the in the rows of identity matrix, you will get this matrix. Similarly, we come to the next case. So 4 and 1 are interchanged and 2 and 3 are interchanged. So the corresponding permutation is 1 4 2 3. So from here you can guess what is the permutation we are looking at. So 1 2 1 3 1 2 1 4 2 3. So whenever you are going to add, so this is odd number. So when you go to odd number, this number n minus 1 by 2, that will be a fixed point. So here 2 is a fixed point because 3 minus 1, so maybe n plus 1 by 2. Yeah, so this is 3 case. So 3 plus 1 by 2 is 2. It is a fixed point. Next time we have 4. We have 4 numbers, so you can split it into 2 2 1 4 2 3. Next time odd, it is 5. 5 plus 1 by 2, uh, I think there is no. This is not correct, but yeah, but you can understand the pattern here. So when you add an odd number, so that should be a fixed point. Remaining thing stays as a 2 cycle. So when you put a 6, then this is 1 6 2 4 3 5. Okay, so try to see the pattern here. And now let's come to the important theory part. So from symmetric group to set of all Nbn permutation matrices, we have a group isomorphism. This is a group matrix group with respect to matrix multiplication. This is permutations, but they are isomorphic group where you send a permutation to corresponding permutation matrix. So since they are isomorphism, order of a permutation is equal to order of the corresponding permutation matrix, but order of all these permutations are 2 because they are product of 2 cycles. Therefore all these matrices also has order 2 in this group. That means that a square equal to identity. In other words, x square minus 1 is the minimal polynomial. Note that x square minus 1 should be the minimal polynomial because a set minimal polynomial of a divides all the polynomials satisfied by a. Therefore, a satisfies x square minus 1. Therefore, minimal polynomial of a should divide x square minus 1. But so why minimal polynomial divides x square minus 1? Why minimal polynomial should be equal to x square minus 1? Because the divisors of x square minus 1 are x minus 1 into x plus 1. Okay, so if this is the minimal polynomial, then the matrix should be identity matrix. If this is the minimal polynomial, the matrix should be minus identity matrix. But we know that none of these matrices are identity or minus identity. Therefore, these are not possible minimal possible. These divisors are not possible as minimal polynomial. Therefore, this polynomial itself should be the minimal polynomial. Okay, let's go to the next problem. Which of the following statements are true? Let a belongs to M3 of R such that a power 4 equal to I, then and a not equal to plus or minus I, then a square plus I equal to 0. Let's see. So it is given that a power 4 equal to I, that means that a satisfies x power 4 minus 1 equal to 0. Therefore, minimum polynomial should divide x power 4 minus 1. But this is x square minus 1 into x square plus 1. Now you consider a matrix for which this is the minimal polynomial. So this is product of distinct linear factors, right? So for example, you consider this 3 by 3 matrix. This polynomial has minimal polynomial x square minus 1. Okay, because I mean, you can directly check x square minus 1 is the minimal polynomial of this polynomial. Therefore, this matrix satisfies this polynomial. Okay, and if you calculate the fourth power of this matrix, you get identity matrix. Okay, so this is an example of a matrix satisfying a power 4 equal to I, but its minimal polynomial is x square minus 1. Therefore, it satisfy uh, x is it's therefore it satisfy a square plus a square minus I equal to 0. Okay, I mean, if this is the minimal polynomial, this factor only it satisfies. This factor it won't satisfy. Okay. Therefore, a square plus I not equal to 0. We can consider this example. Okay, so first option is wrong. You can argue similarly, a cube equal to I, a not equal to I, then a square plus a plus I equal to 0. But you can argue similarly, but this time the answer is true. Let's see why. So it is a 2 by 2 matrix, a cube equal to I, then minimal polynomial should divide x cube minus 1. So the factorization of x minus 1 is x minus 1 into x square plus x plus 1. This cannot be minimal polynomial since this will imply a equal to identity. Therefore, this should be the minimal polynomial. So there you had two choices, but here we are getting this choice is not possible, but this choice is possible for a 2 by 2 matrix. Therefore, this is the minimal polynomial as well as characteristic polynomial. Therefore, a should satisfy a square plus a plus I equal to 0. Now, if it is a 3 by 3 matrix, okay, note that it is a 2 by 2 matrix, then it is different. So, if it is a 3 by 3 matrix, then the option is wrong. Let's see why. A cube equal to I, so minimal polynomial should divide these polynomials. So minimal polynomial, this is not possible. Therefore, a, because that will imply a equal to identity. Therefore, minimal polynomial should be this polynomial x square plus x plus 1. But this cannot be minimal polynomial for a 3 by 3 matrix because roots of this polynomial are primitive third root of unity, complex number. For example, its roots are of the form alpha comma alpha bar. Okay, if this is the minimal polynomial, then the for characteristic polynomial also only these numbers should occur as roots. Okay, but if alpha occurs 2 times, then alpha bar also should occur 2 times. Okay, but then characteristic polynomial will have 4 roots. That is not possible because it is a 3 by 3 matrix. Okay, so we conclude that this polynomial cannot be minimal polynomial because roots of the minimal polynomial and roots of the characteristic polynomial are same. Okay, only multiplicity varies. So by using that argument, if this is minimal polynomial, these are the only distinct values of a 3 by 3 real polynomial, degree 3 real polynomial, but that is not possible. Okay, because the third root has to be a real root. So if it is a real root, then that will be some different number beta, and that beta should occur here also in the minimal polynomial because every root of characteristic polynomial will appear in minimal polynomial also. Therefore, this cannot be the minimal polynomial if it is a 3 by 3 matrix. Okay. So we conclude that this is not a possible minimal polynomial. This is not a possible minimal polynomial. Therefore, the x cube minus 1 minimal polynomial. So yeah, minimal polynomial divides x cube minus 1. So that should be the minimal polynomial. So if it is a 3 by 3 matrix, it means that the minimal polynomial and the characteristic polynomial, all of them equal to x cube minus 1. Okay. So we conclude that this polynomial x square plus x plus 1 a cannot satisfy. Therefore, this option is wrong. Okay. So next problem. Find an orthogonal matrix P such that the diagonal matrix and the diagonal matrix D both in M2 of R such that P transpose AP equal to D. Okay. So what you do, this is a real symmetric matrix. Okay. So you calculate the eigenvalues and eigenvectors, you put the eigenvectors as columns, then you will get this matrix, and that matrix will be always orthogonal if this matrix is symmetric, and the eigenvalues you put it as a diagonal entries, you will get a diagonal matrix. So this is simple. We have seen many times. So I'll skip to the next problem. Which are the following subset of R2 are connected? R2 minus Q cross Q. It is a very very important problem. Many times they asked in the interview. So I have made a video in our channel. Please check this video. R2 minus Q cross Q is even path connected. Okay. So in particular, the same proof we have discussed the more general case also in this video. R2 minus A is path connected, where A is a countably infinite set. So if you know this general result, then in place of A, if you take Q cross Q, which is a countable infinite set, you get R2 minus Q cross Q is path connected. Okay, please check that video in my channel. So first option is true, and the second result is again very interesting. It looks like topology sine curve, but it is not. In topology sine curve, you need in the y-axis from 0 to plus 1, you need that points also. Minus 1 to 1, you need that point in the y-axis, but it is not included. But nevertheless, we can argue in a similar way. So let's see. So 0 comma 0 is a limit point of this set. X comma this uh, 0 comma 0 is a limit point of this set. Okay, let's see why. For example, there is a sequence which is converges to 0 comma 0 from this set. For example, you can consider 1 by n pi comma sine of 1 by n, sine of 1 by 1 by n pi. Okay, so this will be sine n pi, which is 0, and so this term will, this is always 0, and this is 1 by n pi. As n tend to infinity, this goes to 0 comma 0. Therefore there is a sequence which is converges to 0 comma 0. Therefore 0 comma 0 is a limit point of this set. Okay, now this set is a connected set because this set is homeomorphic to open 0 comma infinity. So from here to here, you can there is a 1 continuous function given by projection onto first coordinate. From here to here, you have a continuous function that is sending x goes to x comma sine 1 by x. So that is, since the function sine 1 by x is continuous in open 0 comma infinity, this map is also a 1 continuous function. Okay. Okay. So we get this. This is homeomorphic to 0 comma infinity. Therefore, it is connected. Now, so if A is connected, then A bar is connected. Also, anything lies between A and A bar, that is also connected. Okay. So now you take if you with this set, if you add only this limit point, this is something lies between A and A bar. Okay. Therefore, this set added with this set is connected. Okay. Okay. So option C, set of all xy belongs to R2 such that xy equal to 1 union union x axis. Okay. So if you draw the diagram, you will see that in the positive side, this is the curve xy equal to 1. In the negative side, this is xy equal to 1. And you have to add x-axis also. If you notice clearly, these three parts not touching each other. At infinity, it goes closer and closer, but it is not touching. Okay. Therefore, it is clearly disconnected. So, so we get, sorry, this is connected, but this is not connected. Okay. Okay guys, if you like this video, please click the like button and share with your friends and subscribe to my channel. Thank you.